Hello, this is Jude Socrates. Welcome to video number 16 for my series in multivariables. Okay, so here we are. We have a plate on the XY coordinate system. So it looks like it could be a type 1 region, for example. We have X going from here to here, Y going from down here to up there. Okay, so if this were a piece of cardboard, like this triangle over here, this is something which we could call a homogeneous plate. Okay, so what that means is that if you cut a little square anywhere on this triangle, and as long as the two squares are the same size, then you expect them to have exactly the same mass. Okay, so this plate would have uniform density. Well, what if you had a plate that was a little bit unusual? Okay, so what that means is, if you pick a point on the plate and you cut a small rectangle, okay, with width delta x and height delta y, and you put that little rectangle on a scale, and you repeat that around our lamina, our plate, you're not going to get exactly the same weight, exactly the same mass as you go around that plate. Okay, so in other words, the density of that plate depends on the location, the position of that plate, which is of course given by xy. Okay, so I'm using the notation though that we used when we first constructed the double integral. Okay, so we have a partition along the x, partition along the y, and we have a representative point, xi bar, yj bar, in one of those little rectangles. In this case, it's the midpoint of that rectangle. Okay, so what is this density function? If we make this rectangle smaller and smaller, okay, so if we excise that little portion of that plate and we find its mass on a very sensitive weighing scale, and then we divide by the area of that plate. Okay, and then here's the tough part. We're going to take a limit. Okay, we're just going to imagine it happening, that we make the width and the height of our little rectangle smaller and smaller. Okay, the limit of this ratio is what we call the density function at xy. Okay, so going backwards, if you want to approximate the mass of this little rectangle, then this mass is approximately the density times the area. Okay, so we just move the area over to the other side. Okay, so of course that's just an approximation, but as usual, through the magic of calculus, if we take the limit as the number of subintervals gets smaller and smaller, both along the x and along the y. In other words, the area of that little rectangle gets smaller and smaller, and we add up all of those masses, the density times the area, then we get the exact mass of that plate. All right, so with the magic of calculus, it becomes the double integral of the density function with respect to the area difference. All right, so let's jump into this example. I have this density function, x squared plus 3y, and the plate is bounded by a parabola, an upside down parabola above, and by what looks like a line below. Okay, so we're going to go to GeoGebra for a minute, and we're going to sketch this region, and let's see what our plate looks like. Okay, we have y equals, oops, my apologies, y equals 5 minus x squared over 4. Oh, I'm sorry. This always happens to me. So x squared, and then exit the power divided by 4. Okay, so we have an upside down parabola, and we have y equals 3 minus x over 2. All right, so we have that line. Okay, so we have this region over here. Okay, and we want to find the mass of this region given the density that we have. Okay, I also wanted to show you though, is there another way to draw this so that we can see a shading? Okay, so I'm going to hide these two, and I'm going to show you how to graph inequalities. Okay, because now that we saw that region, we want to see what is below the parabola and what is above the line. Okay, so that's two inequalities. We want 5 minus x squared over 4 to be, I'm sorry, let me put the y over here. We want y to be less than or equal. So I need the keyboard here, and where is my less than or equal? There you are. Okay, so that is the first inequality. But now I need the second inequality, and for that I need a symbol from this part of the keyboard. I need the conjunction symbol. Okay, so that almost looks like the letter A, right? So it's missing the horizontal bar. So that means and. Okay, so I want y less than or equal to that, and I want y to be greater than or equal to, so I need to go back to the symbol keyboard. Yeah, that's the one. Greater than or equal to 3 minus x, woohoo, over 2. All right, so that is our plate. It is now properly shaded. So we want to make an integral on this plate, and it looks like our domain is going from -2 to +4. Okay, if we draw arrows from left to right, going low to high, we are entering on the line and we are exiting on the parabola. Okay, so we're going to do a little bit of algebra. Let's confirm first that our plate starts at -2 and finishes at +4. Okay, let's go back to our word. All right, so we need the intersection of these two equations. So y has to be the same on both equations. So the y for the first equation should be the same as the y for the second equation. Okay, so I think a good idea would be to get rid of the fractions, the 4 and the 2. We can do that by multiplying by 4. So 20 minus x squared equals 12 minus 2x. Okay, and I think we should put everything on the right because I don't like that negative x squared. You probably don't either. And I think 2x should be next to that, and then 12 minus 20, that is minus 8. Do we know how to factor that? Well, we do have good guesses, don't we? The 4 and the minus 2. So we have x minus 4. Does that work? And x plus 2. Yeah. Negative 4x plus 2x gives us minus 2x. Minus 4 times 2 gives us minus 8. Okay. So our suspicions are correct. Our integral will start at -2 and will end at +4. Okay, so we need integral from -2 to +4, and the outer will be dx. We are scanning with type 1. The inner is our dy, and our integral will be from, we said the lower limit is the line, so that's this one. 3 minus x over 2, looks better that way rather than with the fraction, and 5 minus x squared over 4. Okay, and our density is over here. Okay, would you like to see the answer? Yeah, all we have to do is click on that. 117, that is what we need to find. Okay, so let's do it. Okay, our inner antiderivative is with respect to y, so that becomes antiderivative of x squared times y plus 3y squared over 2. Okay, and then we are going to plug in our limits. Okay, so for the upper limit, we will have x squared y, so x squared times 5 minus x squared over 4, 3y squared over 2. So we plug in 5 minus x squared over 4. Okay, so we know how to square a binomial, right? 25 minus 5 over 2x squared plus x to the 4th over 16. We have to divide that by 2, multiply by 3. You know what to do. So I'm just going to click equals, or I think I should say compute and expand. Yeah, okay, that's what we want. We know our algebra. Okay, so similarly for the lower, we need to replace y with 3 minus x over 2. Okay, and the same thing over here. Okay, and then we need to expand. Okay, again, pesky serve. So much algebra. So compute, expand. Ooh, okay, so we have that. And next we have to subtract. So we'll subtract the upper from the lower. I'm sorry, the lower from the upper. So start with the upper, subtract the lower. Don't forget parentheses because we have minuses over there and they are the worst, aren't they? So that is, ooh, exciting. So we have fourth power, third power, second power, and first power, and a constant. Okay, so we have the outer integral now. We will integrate that. We know how to apply the power rule. We'll get x to the 5 cancels with the 5. That's nice. X to the 4th over 8, x cubed over 24, 17 in the numerator. You know what to do. Okay. So do we get 117? Thank you so much. Yeah, of course. We get 117. Okay. So we are going to go a little bit further now. So you remember that triangle that I was holding on to earlier? What we're going to do next is we're going to try to balance this plate that we saw, okay? Except we're going to do it hypothetically because there is no factory in the world that will create a plate with this density. Okay, what is that? Okay, but all you have to do is order something from your friendly internet merchant and you'll get a cardboard box and you can cut out triangles or circles like this. And what we're going to do is we're going to look for the point on the plate where if you put your finger, okay, it's going to be perfectly balanced. Okay, so obviously that is not the middle of the base and that's not the middle of the height either. And if you did this in second semester calculus, you might remember that's 1/3 of the way. Okay, so that distance, you double it and you get to the opposite vertex. Okay, so we're going to take a look at a little bit of physics and we're going to derive some formulas using integrals, double integrals, of course, that will help us to find this center of gravity. All right, so here we are. And if you saw that section about level curves, don't worry. We'll see that at the end of the video. But I thought I'd do this part first. Okay, so that's kind of what I was doing with this triangle. Okay, so we have something a little bit more abstract here. Where will we find this mysterious center of gravity? Okay, so we know how to find the mass, but the physics that we need to understand this balancing act that I did on my finger is the concept called a moment. Okay, so yeah, the idea is basically something that we have kind of known since kindergarten. It has to do with balance. It has to do with rotating around a fulcrum. Okay, so if you have a seesaw, a teeter-totter, the midpoint of that seesaw is the fulcrum of this system. Okay, so you know that if you sit on one end and there's nobody on the other side, of course it's going to tip. Okay, and you will be on the ground. And, you know, you need your big brother or sister to be on the other side so that you would go up, you would rise up. And that's important because if somebody lighter than you, maybe your kid brother or sister, were on the other side, you're going to stay on the ground. Okay? So that's because your moment is greater than their moment. Okay? Your moment is trying to rotate the seesaw in a counterclockwise manner, and their moment is trying to rotate in a clockwise manner. Okay? So let's make this precise. This moment that we are talking about is the product of a force, in this case it's your weight, with the distance of that force from the fulcrum, okay, the axis of rotation, which is over here. Okay, and as far as calculations are concerned, we can put that reference point, that fulcrum, almost anywhere in our diagram. Okay, so we will agree that we will have a sign attached to that moment, positive for a counterclockwise moment, negative for a clockwise moment. When will the seesaw be balanced? It's not going to move, it's not going to rotate when the sum of the moments is equal to, ta-da, 0. Okay, so that's the principle, and that's the equation that we are going to apply in order to find the center of gravity. Okay, so yeah, what does that mean? If somebody lighter than you sits on the other side, you're not going to move. But if somebody heavier were there, then you are going to rise. Okay, so if you don't want to go flying off into outer space, they would have to sit a little bit closer to the center, to the fulcrum. Okay, so why is that? Because their force is bigger than your force, weight in other words. So in order for the product to be equal, the distance has to be smaller. Okay, if their weight is bigger, their distance has to be smaller so that the product will be the same in absolute value as your weight times your distance from the fulcrum. Okay, that is how you balance. Okay, so now let's talk about the physics of balancing this plate. Okay, my finger will be balancing the weight of this plate. Okay, so what we're going to do is to establish references. Okay, here is where my finger is. We are going to consider the x-axis as one of the fulcrums, I guess the plural is fulcra, and the y-axis as another one. Okay, so notice that when the plate wobbles, it kind of wobbles in all directions, okay? Not just left, right, but also front, back, okay? So we will account for that by using these two fulcrums, okay? So with respect to the x-axis, the distance from my finger to the x-axis is y bar, okay? The y-coordinate of the centroid. I'm sorry, I said centroid. We use the word centroid when the plate has uniform density, okay? But in general, we call it the center of gravity. How far is my finger from the y-axis? That's the x-coordinate, so that is x bar, okay? So those are the two distances that we need when we are going to apply the principle of a moment, okay? So the moment produced by your finger with respect to the x-axis is the product of the weight times y bar. How far is your finger from the x-axis? Okay? And similarly, the moment that your finger produces with respect to the y-axis is the product of the weight times x bar. Okay, so now, of course, calculus came in here already because we know that the mass of the plate is already a double integral. Okay, so now, how do we achieve balance? Okay, the individual moments of little pieces of the plate should counterbalance these two moments. Okay, so we already know that a little piece of the plate of width delta x and height delta y has a mass where you multiply the density times delta x, delta y. Okay? How far is this little rectangle from the x-axis? Ooh, that's the y-coordinate again. But this time we'll call it yij star, because that distance is going to change as the rectangle moves around your plate. Okay? Similarly, the moment of that little rectangle is its mass multiplied by its distance from the y-axis, which in this case is the x-coordinate xij star. I have the plate again. We should, of course, notice that the two moments are opposite in direction when it comes to rotation. Your finger, okay, so let's say this is the x-axis. Your finger is trying to push it this way. So from your perspective, it's counterclockwise, okay? But the plate is trying to swing down like this, okay? And from that perspective, of course, it's the opposite direction. Okay, my finger is going up, the weight is going down. Okay, so the two rotations are opposite in orientation. Okay, so one is positive, one is negative. Okay, so we already made the finger moments positive, so the moments for the plate will now be negative. Okay, so same principle. We need the weight of each little rectangle multiplied by its distance from the corresponding axis. So from the x-axis, the distance is yij bar. From the y-axis, the distance is xij bar. Okay? So these two are exactly the same except for the distances. Okay, but of course the total moments are what we are interested in. And as usual, they turn into, tada, a double integral. We add up all of the contributions, we take a double limit, it turns into a double integral. Okay? When do we achieve balance? When the sums of the moments with respect to the x are 0, and the sum for the moments with respect to y is also 0. Okay? So we get this algebraic equation. Notice that there's a common factor of g in both terms. We want 0 so that g disappears. Okay? What are we solving for? We want y bar and we want x bar. Okay, let's put the x bar first, alphabetical order. Okay, solving for x bar, we put this on the other side and we divide by this. Ooh, who is that? That's the mass of our plate. Okay, so by the way, this does have a name. Okay, we just call it m sub y. Okay, so even though moment is supposed to include g, the acceleration due to gravity, we're not going to be so picky about that. Okay, so similarly, your y bar is the double integral of the density with an extra factor of y divided by the mass. Okay, so there are a total of 3 distinct integrals in these two formulas. Okay, so basically it's 3 times the work because we already did the mass. Okay, now we want x bar and y bar. We're going to integrate all over again with an extra factor of x and an extra factor of y. All right, back in the workroom. So we want follow up, find the center of gravity. Okay, it's in the title after all. Okay, so we already did most of the hard work. We found the mass, and that is by using this double integral. Okay. So let's copy that at the bottom. Actually, we do have the answer down there. But more importantly, we need the the setup, okay? Because, yeah, I have the 117 up there. Because we need an extra x over here. Okay? Now, let's think about what we did, right? We integrated this with respect to y. If we have an extra factor of x, though, that's a constant with respect to y. Okay? So what does that mean? If you were doing this in your homework, you don't have to do all of this all over again because there's an extra x there and it just gets multiplied to the final answer over here. because it's a constant with respect to y. Okay, so yeah, let's see if I'm correct. Okay, let's go ahead and find the answer to that. Okay, so I said you don't need to do all of this work all over again for the second integral where there's an extra x, because all of this remains the same. There's just an x hanging out next to it. Okay, so if you do that single integral, will we get the same answer? Oh please, of course. Okay, so therefore the x bar, okay, and yes, I do have a symbol for that. I do have a way to make the bar. So I have to highlight that, and I need, here you go. I believe that's the one. Yeah, that's the one. So we need a regular bar over there. Okay, so yeah, it's pretty close to the symbol. I have a little trick. I put a phantom superscript, and I insert a spacing, a horizontal space, a small thin space. There you go. Haha. So you don't see that space when it's printed in the PDF, but you get this nice gap between the bar and the X. Okay, it's just, it looks ugly without that. So where is the X about? Oh, yes. So one easy way to remember this is if you have that extra X, it gives you the X bar. Okay, so this MY, MX, yeah, don't even go there. Okay, just remember that the X gives you the X bar. So you want 125 there, blah, 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 over 117. Do you simplify? Yeah, you simplify a little bit. So it's a little bit over 1. And our domain, negative 2 to 4. The midpoint is exactly 1. So this is just slightly to the right of the midpoint. Okay. Sadly, of course, you do have to do a lot more work for the y bar. I'm not going to lie to you. Okay? X bar, not too bad. Y, whoops, I'm sorry, what am I doing? No, what did I say? You have to start on the top. This one, this double integral, which I said I'd copy down here, but I forgot. Okay, so this time we have an extra factor of y. Okay, that makes a big difference because now our dy is going to care about that extra y. So you'll have x squared y, which integrates to x squared y squared over 2, plus 3y squared that integrates to, y cubed. Okay, that's nice. Ooh. So now you have a y cubed and you have to cube that, Yeah, sorry. So even if your density function is relatively simple, I mean, what's simpler than this quadratic, just linear. Okay, so yeah, not very interesting, but still already complicated. Okay, so of course we're going to get something very different. Ooh, wow. We're going to get that. And if you want y bar, so I guess I can just copy that, turn that x into a y, yeah. Then we take this answer and divide by our 117. Up, and we get, interesting. So what is that approximately? 3.4. Okay, is 3.4 in our diagram? Let's go over there. Well, yes, it's inside that diagram. So it's like 1 something and 3 something. So it's over there. Center of gravity is over there. Yeah, so if this was actually a manufactured plate with a given density, then that's where you have to put your finger. Okay, so before we end, let's talk about level curves. Okay, the density function is x squared plus 3y. Okay, there's a corner over here. What is x squared plus 3y here? 16 plus 1, 17. Okay, how about here at 0, 5? X squared plus 3y, 15. How about over here? X squared, 4 plus 3y, 12, 16. Okay, so what are we going to do? we are going to draw those level curves by saying x squared plus 3y equals, let's start with 17. Okay. So, why did I say 17? 16 plus, oh, stupid. Not 17, 19. Okay, there we go. So 19 is what we get over here. Oh yeah, I forgot to multiply by 3. That's what happened. Never happened to you, right? Okay. So that has density 19. Keep going back to 17. 19 over there, and nothing else on that plate has density 19. Okay. What did we say here? 4 plus 12, 16, right? So where is the density? Yeah, there we go. Ooh. So there are actually lots of points on the plate where the density is 16. Okay. What about here at 0, 3? Okay, so that's 9, right? Yeah, I actually did it right for a change. Okay, so all the points here inside the plate have density 9. Okay, so let me show you a way by which we can play with that even more. Okay, so we're going to have a slider. So let's just say k equals 12. Ooh, okay. So we got a slider over here. And I'm going to make x squared plus 3y equals k. Ooh, all right. So right now our k is at 12. Okay. You move the slider. Yeah. Oh, it's called a slider because you can slide it left and right. Ooh. So here you go. When you have density 8.5, density 8, is there density? Ooh, 8.3, you're outside of the region. Okay, so it looks like the smallest density is like 8.4 or something. Okay, as you increase the density, okay, these points on the plates are getting heavier and heavier. Okay, because the density is x squared plus 3y. Okay, so yeah, density 13 something, 14 something. Ooh, okay, so we have reached the vertex of our plate. Okay, you can still keep going a little bit. Yeah, there are still some points in the plate with that density. Okay, so these are called level curves. Okay, because we basically have a surface, z equals x squared plus 3y. That's a three-dimensional object that we can graph in 3D, just like our solids. Okay, but we're slicing it with these horizontal planes. So when we do that, we get parabolas. Okay, big surprise. There's an x squared there and a 3y. Solve for y, you get the equation of a parabola. Okay, so we still have points with density 16.3. Little more, yep, we still are getting some points there, and it looks like our biggest density is that corner with density of 19. Okay, so yeah, nothing there. We can also push the play button. Ooh. Okay, so and it goes left, right, and so on. Okay, enough fun. All right, so yeah, many of the diagrams that I'm making for subsequent videos and sections do incorporate a slider, so we can see exactly how triple integrals, ooh gosh, that's where we're going next, how triple integrals behave when you change limits, parameters, all that exciting stuff. Okay, so there you go. Congratulations, you have just finished chapter 2. So when we come back for our next video, we will start chapter 3, which will be triple integrals. Oh wow, chapter 2, double integrals. Chapter 3, triple integrals. Maybe chapter 4 is quadruple integrals. No, just kidding. It's going to stop in terms of complexity at triple integrals. When we do go beyond that, we are going to look at different objects and different kinds of one-dimensional and two-dimensional integrals. All right. So until our next video, where we start our next chapter, I hope you enjoyed this video, and I will see you very, very soon. Bye.